Thank you, Chuyue, and take it away.
Okay, cool. Hi, everyone. My name is Livia. I'm a second-year CS PhD student in Stanford, and I am advised by Barrett. Today, I'm going to talk about our work, Closed-Loop Verifiable Code Generation. This is joint work with Ying, Sheng, and Oded Padon. So, some outline for today. I'm going to begin my talk by introducing the motivation and some background for this work. And then I'm going to introduce the dataset we create for this work. And next, I'm going to talk about specifically how our framework, Clover, works. Next, I'm going to show you how the experiments demonstrate the feasibility of our framework. And to conclude, I will talk about some discussion about the limitations and future work. So I hope this has not become a cliche yet, but I will start my talk by talking about large language model. So LLM has recently demonstrated remarkable capabilities in many applications. And among the many possibilities, their ability to synthesize code from natural language doctrine is stunning. This means that we could potentially be walking into a future where it could potentially enhance the productivities of programmers significantly. So this brings up the natural question, how can we trust the generated code? Formal verification provides mathematically rigorous guarantees on the correctness of code. What if there were a way to automatically apply formal verification to the generated code? This would not only provide a scalable solution, it could also lead to a future in which the generated code is more reliable than human written code. Currently, formal verification is only possible with the aid of time-consuming human expertise. The main hypothesis of Clover is that LLMs are well positioned to generate the collateral needed for formal verification to succeed. Now, how exactly do we do formal verification? First, we construct a mathematical model of the system, and then we provide a formal specification. And finally, we prove that the model satisfies the spec. Right now, step 1 and 3 are pretty much optimized, but traditionally, step 2, it requires significant human expertise to ensure the spec's correctness. There are two key insights moving forward. The first one is that it's simply a shift in perspective. And the result of any AI-based code generation technique should aim not only generate code, but also formal specification with a natural language doctrine. The second insight is that given these components, we can then use formal tools coupled with generative AI techniques to ensure that they are all consistent. So our contribution, Clover proposed a solution for a trustworthy code generation in which we reduce the problem of checking code correctness to checking consistency among code, annotation, and docstring. Second, we also introduce a new dataset called CloverBench, in which we introduce 60 handcrafted Dafny' examples with docstrings. And finally, we conducted an evaluation of the Clover framework using GPT-4 and Dafny'. And our results show that GPT-4 understands Dafny', at least at our dataset level. And then the consistency checks are pretty promising, in which we show that with 10 independent tries, we are able to accept 87 of the ground truth examples. So we name our approach Clover, short for Closed-Loop Verifiable Code Generation. And we predict that Clover, coupled with steadily improving generative AI and formal tools, will enable a future in which the automatic scalable generation of formally verifiable code is possible. There are two phases of the Clover paradigm. In the first generation phase, some process is needed to create the code annotated with a formal specification accompanied by a natural language docstring. In the second verification phase, a series of consistent checks are applied to the code annotation docstring. The Clover hypothesis is that if all of the 6 consistency checks pass, then first, the code is functionally correct with respect to the annotation, and second, the annotation captures the full functionality of the code, and third, the docstring also accurately reflects the functionality of the code. The idea is that we can unleash the powerful generative AI technique in the generation phase and then use the verification phase as a strong filter that only approves of the formally verified, accurately documented, and internally consistent code. There have been many popular datasets for code generation in different domains, but none contain annotation or use the Dafny language. We want to carefully curate the program used to test our first prototype. So for these reasons, we introduced a new handcrafted dataset called CloverBench. We expect to add and improve it over time. Currently, it has 60 small handwritten Dafny examples that you might find in standard CS textbook in standard CS intro textbooks. We are also working on adding support for other verification frameworks and languages such as Barrett and Rust. For each program, there are 4 variants. The first one is the ground truth variant, whose code annotation and docstring are all consistent. There are also 3 incorrect variants where we either mutate the code docstring or the annotation. Associated with each example, there is a set of unit tests. As an example, you see here, this is a fully annotated ground truth Dafny examples. Let's take a closer look at how Clover works. Clover expects the output of the generation phase to contain 3 components: code, annotation, and docstring. The verification phase checks the consistency of every pair of the component and succeeds only if all checks pass. One key idea used to check the consistency between components is reconstruction testing. Given these 3 components as input, we try to reconstruct one single component from one other single component out of the 3. And the check only passes if the reconstructed component is equivalent to the original one. We do this for 5 out of the 6 directed edges. One special case is checking that the code conforms to the annotation, in which we use deductive verification tools. And in our case, we use Dafny. So the annotation soundness edge, a deductive verification tool, is used to check that the code satisfies the annotation. The annotation completeness edge, given the annotation, we use an LLM to generate new code, and then we check that the generated code is equivalent to the original one using unit tests. For anno to doc edge, an LLM is asked to generate a new docstring from the annotation, and then the 2 docstrings are checked for semantic equivalence using an LLM. For the doc to anno edge, we generate a new set of annotations from the original docstring, and then we use the verifier to verify that the 2 set of annotations are equivalent. For the doc to code edge, an LM is asked to generate a new code, and the unit test is used to check for 2 code equivalence. Finally, for the doc to code edge, the new docstring is generated by an LM, and then also the same LM is asked to check if the 2 docstrings are semantically equivalent. For the experiments, the first question we wish to answer is, can GPT-4 generate reasonably good Dafny code and annotation. Recall the integer square root example that you saw earlier. So if we use this as an input to an GPT-4 and we ask it to generate a full set of annotations, it's actually able to succeed in one try. The example you see on the right, it can pass the Dafny verifier. For a more complicated example, such as this one, it's checking if all the characters in a string are digits. If we use this one as input, for the first try, GPT-4 gives a syntactically wrong answer. But if we feedback the Dafny compiler feedback, it's actually able to fix itself. And what you see here is correct and verified by Dafny. For even more complicated examples, such as this one, this is saying that we return a new array that contains only the even numbers of the input array. It's unable to get it under 3 tries. But just for reference, this is a fully annotated version of the function that you just saw. I think it's unreasonable to expect GPT-4 to return this answer. So to conclude, can GPT-4 generate good Dafny code and annotation? Although not perfect, out of the box, GPT-4 can produce some correct annotations for the majority of programs in our simple set of configurations. This suggests that using LLM for specification generation is feasible, and we expect that further efforts in these directions, including fine-tuning for specific tasks, will likely lead to even stronger capabilities. So as mentioned before, each program in our dataset, we created 3 incorrect variants. For the first one, we mutate the annotation and keep the docstring code the same. For the second one, we mutate the docstring. And for the last one, we keep the docstring the same, but we mutate the annotation and the code in a way that the Dafny verifier still pass, but it's inconsistent with the docstring. And our main experiments will evaluate the capabilities of the Clover consistency checking algorithm. For each example in the CloverBench, we run all 6 consistency checks using 3 tries with maximum feedback from Dafny verifier or compiler wherever possible. We also evaluated the effect of multiple independent runs, meaning that we repeat each of the 6 checks the number of k times. If any of the k attempts succeed, we consider the check to pass. We see that when k equals 10, it has 87 acceptance rates for the correct one, and we maintain 100 rejection rate for the wrong variants. So this table shows the result of 6 checks for each wrong category. We observe that the doc2Anno has the highest rejection rate. This is because the annotation equivalence checking is very strong, because we use the Dafny verifier, and this will guarantee that only logical equivalent annotations are accepted. Overall, there are no false positives. Of course, there are still many limitations to the framework. Firstly, the capabilities of LLM can still be improved. And right now, our annotation only specify functional properties. This means that we cannot enforce any implementation detail checking or to check if a particular kind of optimization still pass the functional correctness. Also, there could be a case where the LLM is internally consistent, but it's misaligned with human intention. For example, because the natural language is ambiguous, the LLM could have a different understanding of the property with what we understand. Finally, right now the CloverBench only contains very small self-contained examples. This means that we have not yet proved the CloverBench's capabilities on larger code base, where it includes some intra-procedure calls and multiple layers of function calls. So to conclude, we introduced Clover, which reduced the problem of checking generated code correctness to consistency. And we also introduced a new dataset that features 60 textbook algorithms written in Dafny'. And after performing our consistency checking on the dataset, we see that it's pretty promising with a 87 acceptance rate for the correct one and perfect rejection rate for incorrect examples. For the future work, we believe that better verification tools, improved LLM generation capabilities, and better equivalence checking can all improve the performance of the Clover framework. We also plan to scale to larger code base. This means that we will extend our framework to verify intra-procedure calls and also extend our context window for verifying function calls. Thank you. This is my talk for today.
You mentioned the LLM can sometimes generate a better program after you give it feedback from the compiler about an error in a previously generated program. I'm wondering, since you're working with verification, you could also provide a counterexample for an incorrect program and pass that back to the LLM to tell it, hey, this is the sample for which the program is incorrect. Do you think that could help the generation?
Yes, definitely. I think any kind of feedback will be helpful. But in a case of Dafny', because the counterexample it provides, it's not even very readable by humans. So LLM has an even worse understanding of the problem. So I think right now the capabilities of LLM it's only good enough to understand simple compiler feedback, where you directly tell it where the problem is. And the problem with counterexample is that it involves some logical reasoning, so I don't think right now it's able to guide it to fix itself.
Okay, thanks.
Am I understanding correctly that CloverBench, the programs in it is the program text, but without the specifications?
It has it has all degrees of annotated programs.
Okay.
So the most detailed one, it has docstring, full annotation, and the code.
And when you run your tool to generate things, have you ever tried to generate the code instead of that is keep the specifications and generate the code instead of the example you showed?
Yeah, here. So yes, we did try code generation. It's actually
okay, great.
It's actually easier than annotation generation. So here you see that the code generation, it has a higher pass rate than annotation.
Oh, great. Thanks.
Hi, so it's a two-part question. So how large are the programs, and have you studied if there is any correlation with like increasing number of lines of code or variable count with success rate?
So for a CloverBench, it's around 10 to 30 lines of code. And definitely, I think because of many reasons, including like LM parse window for a context and its ability to understand things, with the increase of line of code, the capability dramatically drops. So I think if the success rate will be very low after 50 lines of code, if it's a non-contaminated example.
Like instead of lines of code, we can increase the number of variables by trying to keep the lines of code similar, or increase the number of nonlinear operations or something like that, and see if that causes difference in success rates.
I think with LM, it's more a problem of has it seen the example before. So if even if it's a very complex example, but a very classical one with many nonlinear operations, it's able to give back very good answer.
So for things that are protocols and stuff which have never been verified yet, so for that it will probably not work.
I think for protocols very specific to policies, then it's not able to give very good answers as the complexity increases.
Thanks.
Okay, let's thank the speaker again.